In this screencast, we are going to talk about different gas laws and work some example problems. The first gas law we're going to talk about is Boyle's law. I have an image here of the British chemist Robert Boyle, and he observed that volume of a given amount of gas is inversely proportional to its pressure at constant temperature. So he said, look, volume, which we are going to represent with a V, decreases as pressure, which we represent with a P, increases. And so we say if one thing goes up and the other thing goes down, this is inversely proportional. And likewise, if volume were to increase, then what you're going to see is pressure is going to decrease. And so one of the ways we can mathematically represent this is we can say, look, pressure is inversely proportional to the volume. And another way of saying this is the pressure and volume equal some sort of constant. Okay. Now, what's really important here, and I want you to recognize this, is that temperature and the number of moles, or the amount of the gas, and we're going to represent that with an N, are constant. And that means they don't change. Okay? Now, we experience this every day when we breathe. So when we look at this image, when we inhale air, right, our diaphragm, which is right here, moves down, right? It contracts. And the volume of the chest cavity increases, and that reduces the pressure in our lungs. And so the pressure in our lungs is less than the outside air, and it causes external air to rush in to equalize that pressure, and that's how we inhale. When we exhale, the diaphragm moves up, decreasing the chest cavity volume, and it increases the air pressure in the lungs, and it causes the air pressure to rush out into the atmosphere. So this is a great example of Boyle's law. Now, the next law we're going to talk about is Charles' law. This is named for the French scientist Jacques Charles, who documented the linear relationship between volume and temperature. And so what he says is that, look, as the temperature increases, the volume also increases. So, right, so this is directly proportional. Or as the temperature decreases, the volume is also going to decrease. You can see this on a hot day. If you live in a neighborhood where people put balloons out for birthday parties or big events, and you're driving through the neighborhood and it's a hot day and they put the balloons out when it's cooler in the morning or the night before, sometimes those balloons will explode. You can also see this at some car dealerships. So it's just kind of interesting there. If you love crafts, then this shows this graphically where the temperature is increasing and the volume increases as well. Okay. Next gas law we're going to talk about is Avogadro's law. Now, you may remember him from Avogadro's number. And what he determined was the volumes directly proportional to the number of moles of gas. And so what this means is, as the number of moles of gas increase, right, the volume also increases. So it's directly proportional. Same thing. If the number of moles of gas decrease, the volume also decreases. And you can see this if you like graphs. You can see this here. You can think about blowing up a balloon, right? If you have 1 mole of helium, here's the volume. If you have 2 moles of helium, it's twice as large, right? So it's a lot larger. One of the ways that we can represent this is by saying V over N equals a constant. And then the next gas law we're going to talk about is Amont's law or Gay-Lussac's law. There's a little bit of disagreement in the scientific community about who this law should actually be named after. That's why I give you both the names, right? And what this law says is pressure is proportional to the temperature for a fixed quantity of gas at constant volume, right? So what that means is, hey, look, as the pressure increases, right, the temperature also increases, or as the temperature increases, the pressure increases. As the pressure decreases, the temperature also decreases. And so this can be shown as PT equals a constant. So everything so far, when we talk about all of these different laws, have been directly proportional except for Boyle's law. So that leads us to a combination of all of these laws, which is the ideal gas law. Let's look at the gas laws as we talked about them. So we have Boyle's law, which says that PV equals some constant. And then we have Charles' law, which says V over T equals a constant, but another way to write that would be V equals some sort of constant multiplied by temperature, okay? And then we have Avogadro's law, which we said was V over N equals a constant, but another way to write that would be V equals a constant times N, which is the number of moles. And then we have Montan's law, or Gay-Lussac's law, where we said, look, that's pressure over temperature. Basically, we could say, look, pressure equals a constant times some temperature. Now, if we were to look at all of these, right, we can see here there's a common thread. There's a constant here, right? And that constant, right, if we were to combine all these to make the ideal gas law, you would see that we've got pressure on this side. You can see pressure. You have volume on this side, and then it equals some sort of constant. That constant is R, and then we have the number of moles times T. So when we talk about the constant, that is R, and that equals 0.08206 liters times ATM over moles times Kelvin. Now, this is called the ideal gas law. You can, if you just know this, I'm going to show you how to do it. If you just know this, you can figure out Boyle's law, Charles' law, Avogadro's law, and Montan or Gay-Lussac's law from the ideal gas law. And that's something that we can look at. I want to point out one other law really quick, and that is the combined gas law. And basically, people refer to the combined gas law if you have two sets of conditions, right? And the number of moles are constant. Then you can say the pressure at one set of conditions times the volume at one set of conditions over the temperature at one set of conditions equals the pressure at a second set of conditions times the volume at a second set times the temperature at a second set. And that is called the combined gas law. You can also see that you can set the ideal gas law up like that. And so let's look at that. You have pressure at one set of conditions and volume at one set. And then we can divide by the number of moles at one set and temperature at one set, and that equals R, which is a constant. And if we have pressure at a second set of conditions and volume at a second set and the number of moles at a second set and the temperature at a second set, right, that still has to equal R. So you can set these two equal to each other and have P1 V1 over N1 T1 equals P2 V2 over N2 T2. These two equations are going to be the equations that you absolutely need to know. We're going to work some problems with these here in a second. I want to point out that you can also do stoichiometry calculations using gases. It depends on the mole or mole ratios of reactants and products, right? So the moles of the gas can be calculated if the pressure, temperature, and volume are known. And so that's something that we can rearrange PV equals nRT using algebra, right? Just divide both sides by RT and we can figure out the number of moles. And then we can use that in any type of stoichiometry calculations. So let's do some examples. A balloon is partially inflated with 5 liters of helium at sea level where the atmospheric pressure is 1 atm. The balloon ascends to an altitude of 1,600 meters where the pressure is 0.83 atm. What volume of the balloon at a higher altitude? What is the volume of the balloon at a higher altitude if the temperature of the helium does not change during the ascent? There's a lot of words here. And so what we want to do is we want to pick out our really important context clues. And so the really important context clues with pressure calculations are going to be pressure, volume, number of moles, and temperature. And there's two things you can look for. One is a value for these, and the other is if these are constant. And so let's look at this. It says a balloon is partially inflated with 5 liters of helium. So 5 liters of helium, that's a volume measurement. And so we're going to come here, we're going to say, great, that we know a volume measurement, that's 5 liters. And the atmospheric pressure is 1 atm. And so that pressure equals 1 atm, okay? The balloon ascends to an altitude of 1,600 meters where the pressure is 0.83 atm. All right, here's where we stop and we say, okay, hey, look, I've been given 2 pressures. That means I have 2 sets of conditions. And so this volume and pressure were at the same set of conditions. They were at the same time. Context clues that tell us that are, it was 5 grams of helium at sea level where the atmospheric pressure is 1 atm. That means these 2 things are tied together and the balloon ascends to an altitude of 1,600 meters where the pressure is 0.83 atm. What is the volume of the balloon at the higher altitude? So we are looking for the second volume here, and it tells us the temperature doesn't change. And so that means the temperature is constant because it doesn't change. And then the number of moles isn't even mentioned, so we can assume that the number of moles is also constant. So because you have 2 sets of conditions, you want to set up the ideal gas law, P1V1 over N1 T1 equals P2 V2 over N2 T2. And you want to cross out anything that is constant. So we're going to cross out the number of moles. We're going to cross out the temperature because those are constant. And now we have P1 V1 equals P2 V2. I like to square what I'm solving for. So I'm solving for V2, and that means mathematically, I want to get it by itself on one side of the equal sign. So to do this, I'm going to divide both sides by P2, okay? We see then that P2 cancels out here. So now we have P1 V1 over P2 equals V2. Okay. And we just plug and chug. We're just going to plug in the numbers where they go. We have 1 atm times 5 liters divided by 0.83 atm, right? And that should equal our V2. Now, we've got a great double check. Our pressure units should cancel. We should be left with units of volume, which is liters. So now I'm going to pick up my calculator and I'm going to be cognizant of the correct number of significant figures here. I want us to notice that this value has 2 significant figures. Both of these have 3 significant figures, so our answer needs to be reported in 2 significant figures. And what we see here is the answer is 6 liters. Now, let me tell you, I love gas law problems, and it's because there's a great double check. Excuse me, so let's look, right? What we have happening here between our 2 pressures is pressure here is decreasing, right? And we know from Boyle's law that if the pressure decreases, the volume should increase. And so we can check that. And our volume is going from 5 liters to 6 liters. And so this tells us that our volume is in fact increasing, and that Boyle's law is the law that this applies to. So it's a great double check, and you can keep that in mind as you work through some of these problems. Let's do another problem. Let's do another gas law problem. So here's the second example. Evan was drawn to the study of gases because his interest in hot air balloons. What temperature in degrees Celsius is required to increase the volume of a sealed balloon from 2 liters to 3 liters if the initial temperature is 15 degrees and the atmospheric pressure is constant? So when we look at this, it says, what's the temperature in degrees Celsius is required to increase the volume? So it's asking us for the temperature, right? And it's saying, hey, we want to increase the volume from 2 liters to 3 liters, okay? If the initial temperature is 15 degrees Celsius and the atmospheric pressure is constant. So we're given a volume of the gas, which is 2 liters. That's what it is initially. And the temperature here initially is 15 degrees Celsius, okay? We look here at the second volume, right? And that's 3 liters. And then it's asking us for the second temperature, okay? When you do things with temperature in gas law problems, you must convert to Kelvin every time. So I'm going to come here and I'm going to use the 273 value to convert to Kelvin, okay? And so that gives us 288, right? And when we do this, right, we're going to say, all right, we got P1 V1 equals P2 V2 over N1 T1 for N2 T2. And we're going to come here and we're going to say, okay, it's only talking about temperature and volume. So that means my pressure is going to be constant and my number of moles are going to be constant. So the equation I'm going to use is V1 over T1 equals V2 over T2. So when we look at this, we are trying to get T2 right here all by itself. So there's a couple different ways you can do this. I'm going to show you the way I like the best. You multiply both sides by T2 and you get rid of it here. And then you rewrite it as T2 V1 over T1 equals V2. Then you multiply this side by T1 and you get rid of that there. And so now you have T2 V1 equals V2 T1, and then you divide both sides by V1. Okay, that's what I particularly like. There are a lot of different ways to do this. Choose the way that makes the most sense to you. Okay, so we have our equation here, and so now all we have to do is plug values in. And so T2 equals V2, which is 3 liters, times T1, which is 288 Kelvin, over V1, which is 2 liters. When you do this math to the proper number of significant figures, you get 432 Kelvin. Now, the question asks for this in the temperature in degrees Celsius. And so we want to convert from Kelvin to degrees Celsius. So we just subtract 273, and that gives us 159 degrees Celsius. And so that's what we see there. Now, this is an example of Charles' law, right? Where what we see here is the volume is increasing. So because volume and temperature are directly proportional, you would expect to see the temperature increase. So the temperature is at 288 Kelvin, and we see that now the temperature is at 432 Kelvin. So that's a great double check. So again, we're using our knowledge of individual gas laws to help us predict what the, or just double check really, not predict, but double check what our answers will be. Let's do another example. Calculate the pressure of 1.2 moles of methane gas in a 3.3 liter container at 25 degrees Celsius. Now, let's look at the context clues here. We have pressure. We're asked to calculate the pressure. We're given moles, so that means we know our number of moles is 1.2 moles. We have a 3.3 liter container. We know that's our volume. And then we have a temperature here. That temperature is 25 degrees Celsius. I'm going to go ahead and add 273 Kelvin because I always forget. And so I like to go ahead and get that out of the way so I don't forget to convert. And so we're looking for pressure. We have moles, volume, and temperature. We do not have two conditions here. And so that means we are going to use the Pivnert equation, or PV equals nRT. Okay. And what we want to do is we want to get pressure by itself because that's what we're solving for. So to do that, we're going to divide both sides by the volume. And now our pressure equals the number of moles times the gas law constant times temperature over volume. And so that gives us 1.2 moles. Okay. And we're going to have the gas law constant here. You can, you do not have to memorize this. It will be given to you. Well, there we go. Times the temperature, which is 298 Kelvin, over the volume here, which is 3.3 liters. All right, now let's check and do a double check and make sure our units cancel. We've got moles in the numerator here, and we have moles in the denominator of a numerator, which means a lot of times they are down in the denominator. But for ease, I just showed it like this. So the moles cancel. We have Kelvin, same kind of deal. The Kelvin cancels. And then we have liters here that will cancel with the liters there. So we're left with ATM, which is our unit of pressure. So that's our double check. When we do this, we need an answer in two significant figures. And so when you do this math, you should get 8.9 ATM. And that's our pressure. Let's do one other gas law example. So in this one, it says oxygen generators in some airplanes are based on the chemical reaction between solid sodium chlorate, and we've got the molar mass here of 106.44 grams per mole, and iron. And there's a balanced equation. The resultant O2 is blended with cabin air to provide 10 to 15 minutes of breathable air for passengers. How many grams of NaClO3 are needed in a typical generator to produce 125 liters of O2 gas at 1 ATM and 20 degrees Celsius? Now, I don't know about you, but I didn't realize that we would only get, if we were flying and those little masks came down, we would only get cabin air for 10 to 15 minutes. So that's somewhat a terrifying aside today. But we're gonna ignore that for just this moment and solve the gas law problem. So when we look through this, a few things, right? We are given the volume of O2. It's right there. So we have the volume, and that's 125 liters of O2. We have the pressure, that's 1 atm. And we have the temperature, and that's 20 degrees Celsius. And I'm going to go ahead and add 273 because I always forget to do that. And that should give me 293 Kelvin. Okay. And it's saying, look, how many grams of NaClO3 do you need? All of this information is for the O2 gas. This is right here. This is what you want to form, right? But this is your starting material. And so we want to know how many grams of NaClO3 do we need to put in this airplane to keep everybody alive if there's an incident. So what we're going to do is we are going to solve, and that's crooked and that is going to drive me bonkers. Okay, we are going to solve for our moles. Well, that's exciting. We're going to solve for our moles of O2 using PIVNR, PV equals nRT. Then we are going to use the mole ratio to determine the moles of NaClO3, right? And then from the mole ratio, we're going to convert the moles of NaClO3 to grams. Okay, so here we go. 1, 2, and 3. So we can solve this problem in 3 steps. And really, we can combine 2 and 3. So I'll show you how to do that. All right. So PV equals nRT. We are going to get N all by itself. And so we can say, look, PV over RT equals N. That's the number of moles that we have. And so what we're going to do then is we're going to say, great, my pressure is 1 atm times the volume, which is 125 liters, over R, which will be given to you, it's 0.08206 liters times atm, over moles times Kelvin, right, times 293 Kelvin. We double check that things cancel. ATMs cancel there. One's in the numerator and one's in the denominator. Same deal with liters. And then our Kelvin cancel. Now this mole is the denominator of a denominator, so it's going to flip up to the numerator. When you do this math, you should get 5.20 moles of O2. Okay? And so this is number 1. That's step 1. Now we're going to do steps 2 and 3 right there together. We're going to use the mole ratio to determine the moles of NaClO3. So we're going to say, look, we need 5.20 moles of O2 to keep the people in the airplane alive for 10 to 15 minutes, or at least keep them from passing out, right? And so we know there's a 1-to-1 mole ratio because we look at the balanced equation and we say, look, there's 1 mole of O2 per 1 mole of NaClO3, right? And then we come here and we say, all right, we know the molar mass of NaClO3. It's 106.44 grams of NaClO3 over 1 mole of NaClO3. And when you do this, your double check, of course, is your moles of O2 cancel, your moles of NaClO3 cancel, and you're left with grams, which is what the problem's asking for. So we take 5.20, we multiply by 1.06.44, the mole ratio is 1-to-1, and so we have 553 grams of NaClO3 that we need to put in that airplane to keep everyone alive. All right, if you have any questions, please feel free to stop by my office. I would be happy to help.